dry saturated pH, but this probably is only so okay, steam is applied dry saturated. So it means that it is a saturated state and it is dry. It means that it is saturated vapor. Okay, so that's what it means. So dry saturated here pretty much means saturated vapor. Okay, so at 4 megapascal, 是我的turbine, and the condenser pressure is 3.5 kilopascal. So just by looking at this question, it actually pretty much covers everything in this room. Okay, so if the plant operates on basic ideal rating cycle, we also so this one is the question that we have to calculate per kilogram of steam. So you need to find everything in terms of quantity. So the second equation, and the output will require so we look at this question first. So if you are asked to draw the TES so this is the focus more on TES. So this is a very simple drawing. You just need two parallel lines. So the top one will be 4 megapascal. The bottom one 3.5 kilopascal. So yeah, all that is the ideal cycle. So which means that everything so here I from line here, then it goes here since it enters the turbine as saturated vapor. So here we also calculate that atmosphere here. So it goes here, then back. So 1, 2, 3, 4. This is pretty much how it looks like. Okay, so question 1 asks for work output impacting the fuel cost. So we are only interested in the work output. Okay, now one thing here. If I draw this in the exam, I will get someone to go because don't forget to draw. You can use the small letter version to find it. So this is small and then this is small. So don't forget all the energy interaction. Okay, so 1 and 2 basically ask you to look for all work. So work out by working. So here is the divided work output. So we want the work output for turbine only. Okay. So let's look at this. So the first one should be very straightforward. Now I won't go the normal route, I'll follow the question. So the question asks for work output first. So look, we can ask for this one. Or sometimes some work is you see a direct work turbine. Okay, so look for out. So work out means that you want stage 3 minus stage 4. So from here you need to find their value. So you know that E3 is 4 megapascal. So dry saturated vapor. So H here will be H3. And then of course you need S3. So once you have this, you move to state 4. So state 4 will be T4 equals to 3.5 kilopascal. And logically speaking, even if you don't check, you know that this is a saturated mixture because 3 is already saturated vapor. So there's no way where it goes horizontally down, vertically down, that it will reach any other state. It will definitely be saturated mixture. So here is the mixture. Mixture is not enough for you to calculate the value because knowing the phase here doesn't really help. So we know S4 equals to S3. So from here you can find X4. And then from here you get H4. Okay, so S4 will be based on S3 or maybe so here S3 is sitting so here you find Then for 2, I will just continue writing first. So for 2, question 2, so for working or work out. So this will be 2 minus this 1. Technically, you already 2 minus 1, so 1 here. So we also know that this equation is T1, T2 minus T1. Okay, I'll just write 2 here. This is the most common equation. So we know that T1 is 3.5 kilopascal. Say true. Okay. So again, this one regardless of whether this is ideal or actual, we always assume this is the case on this. Nothing is in the question. Okay, so to this way, then here we can get H1, and you can get B1. Actually, that's all. Because now you have enough information to start in, you can get work in, then you can also get H2 plus the microgram. You don't really need H2 for this question, but you need H2 for the next question. So, we are working and H2 you have enough. So 3 says that the you need to find the heat transfer to the condenser cooling water and the amount of cooling water required through the condenser if the temperature rise of the water between 55 or 5 Kelvin. So here you know actually 4 is kind of oh yeah, it's still out. Okay, never mind. So 3, this water mentioned in this question is not the water circulating in the cycle itself. So you need to be clear here. You can see that it says that the heat transfer to the condenser to cooling water. The condenser function is to cool down the condenser, right? So what it is trying to say here is this. So if you look at the condenser, so you have a condenser here. At the same time, you have, let's say, you have a cooling water that goes through here. And so this condenser will reject heat to the cooling water, and the water that cools down is, and during the cooling process, the water will increase temperature by 5.5 Kelvin. Okay, so this is what the question is saying. So now here, very straightforward. We know that Q out is H4 minus H1. This one is not. If you know this, you know that. So this Q out is from the condenser. So for the same, so this one, it is an example of a heat exchanger. So the heat comes from condenser goes to the cooling water. So the change of the cooling water, the heat that the cooling water receives. So that's it. That's the point. Right here, water is now. So in this case, what you have to do is you need to use MCLRT. Okay. Now, remember this. Last semester when I teach Thermo, I will try to use MCLRT for water. So let's say if you have let's say like you have T water 1 or you have T water 2, so you get that right now. You can use the enthalpy directly. Then you don't use MCLRT. MCLRT is fine. But in this case, you have no choice because what you know is the temperature change. You do not know their actual temperature, so you can't use the H in this case. So you have no choice. So you have to use MCLRT. So C for water will be 4.18. That's the general value for water. Because this will always be a compressed water. So compressed water. So this will be 4.18. This is 5.5. So from here you can find the amount of cooling water here. Now, you might notice that the unit here is a little bit different. The QR is actually in terms of this. While if you use MCLRT, what you get is joule. Okay. So now the question also asks you need to calculate this for 1 kilogram of steam in the reacting cycle. So here you need to find, so it's a bit weird, but your math will be in terms of per kg also, but it's in terms of per kg of the weight per steam in the reacting cycle. So the kg itself doesn't get so here, if you calculate, you will get that this answer is value. Okay, if you use the small Q of the top. So this is, so it will be something like this. So cooling water per kilogram of steam. So for every kilogram of the steam that pass through the cycle, you will need 74 kilograms of cooling water cooled down. That's what it is. So even though the unit is slightly different, but that is actually or if it is a bit harder to understand that the Q out, you can also use Q out equals to M-4 minus 1 and M-1 kg. The meaning is the same because you are still calculating for 1 kg. Everyone there? So 4 is actually heat supply to the system. So it's actually QA. So QA is the ratio. Then 5 is thermal efficiency of the reacting cycle. So this you can use Q out or Q in, or you can use work net over Q in. You have the same answer. So 4 and 5, basic question. This one you should be able to solve. So steam is supplied to, oh by the way, don't forget I'm just done. So problem 2, steam is supplied to a 2-stage turbine at 4 megapascal, 350 Celsius. In essence, so actually the first part is also the same as in essence, in the first turbine, until it just dry saturated, and then it is reheated to 350 degrees Celsius and expanded through the second steam turbine. So this is actually a reheat question. Just to have two turbine here. So the condenser pressure is 3.5 kilopascal. So actually same as the previous one. Calculate the work output and the heat supply per kilogram of steam for the plant, assuming ideal processes and neglecting the feed pump term. Calculate also the cycle efficiency. Okay, so this question has a very interesting assumption here, whereby you ask you to neglect the feed pump, meaning it is asking you to neglect the working point. Okay. So how do we do this? Let's try to analyze this cycle first. Okay. Okay. So here once again we draw PS diagram. So this time this PS diagram has three pressure levels. Now, if you are afraid that you will look in messy, you will have the second line you can just draw somewhere over here, but you can draw the figures you already need. But that's up to you, okay? But so here same thing. So when it reaches here, it comes down here. Okay, this one not exactly a very accurate estimation, but okay, so we should know something like this. So 1, 2, 3. So this 3 should go down. The 4 should be at the saturated vapor line because the question says that it's expanded until it just dry saturated. Then you reheat it back to 350 degrees Celsius. So this level should be about the same. I know it's not exactly that. Okay, let me roll it. It's not necessarily always saturated mixture. There is a chance that it might be saturated vapor or superheated steam. So now, like in this case, right, we don't really know which it is in yet. So if let's say the question which is looking at all the time, I always ask you to draw this or sketch this before you calculate. It is okay where you landed as long as it doesn't go too ridiculous. Okay, because we are just sketching, we don't know what to say yet. But of course, if the question is like one of the examples where I tell you that the exit of the turbine should be, let's say 90% quality, then of course when you draw, keep it inside the line. But otherwise, like this case, you don't really know. Then it's like you can just draw this roughly that this diagram is not exactly the best because the line is not very straight. But you know what I mean, okay? So here I'm not writing the whole thing out because I draw very small, so it will be a bit messy if I draw all the line. But don't forget that when you are doing the reheat cycle, you will have 2 keep in, you also have 2 hold out. Okay, so the first one is 4 megapascal. The other one, it doesn't say which pressure, but you know that temperature is 350 degrees Celsius and 3.5 kilopascal. Okay, so again, since the question asks you to calculate the work output and the heat supply per kilo heat supply, so we start from the right hand side first. So the right hand side, you know that T3 is 4 megapascal and T3 is 3 For state 4, we know that S4 equals to S3. This time we do know one additional information. This is saturated vapor. So for this question, you scour through the table, look, cross check the S4 with all the SG value because you want the saturated vapor value to see at which pressure it is at. Okay, because you want the pressure because we know because like okay, let's say you don't know what to find first. You know that we need H4 there. Okay, that's all we know for now. So then we move on to state 5. So when you move on to state 5, you will see that you know that T5 is 350 degrees Celsius. You need one more information. And that one more information that you know T5 is equal to T4. Which means so now you can go back to the state 4. Because okay, so like I said, you don't know what you know, you want for state 4, so you know that enthalpy is always the thing that you need. So you always find enthalpy regardless. You don't know what to do, find enthalpy first. So now we don't know what to do for state 4, so we move on to state 5. So state 5, we know T5 is 350, then now T5 is T4. So we need to go back here, we write down T5 as well. If you attend this, you should know that this is approximately 1000. I forgot whether it's exact or approximately, but yeah. Approximate. Okay, so then now you know both, then you can write H5 as well as S5. Then after that, it's actually the same as what you did for the previous question. So we know that E6 is 3.5 kilopascal, S6 is S5. So from here, S, you can use S6 to find X6. Then H6. So from here, we can solve the first part of the question where we ask for total output per kilogram of steam. So for the total output, don't forget the two turbines, so it will be H3 minus H4 plus H5 minus H6. So this will give you an answer. Okay, so far okay, right? Then we move on to the tricky part here, or the interesting part. So the next thing that we have to calculate is the heat supplied per kilogram of steam for the plant. Meaning, we are looking for Q in, right? And Q in will be H5 minus H4 plus H3 minus H2, or you want to write H2 minus H2. Okay, so now we know that we know H5 now, we know we have H4, we also have H3. So what is the same here is H2? So then now we finally move back to this side. So how do we solve this side? Anyone has any idea? Anyone try this? Yeah, so we look at this one first. So T1 is 3.5 kilopascal. So this one you can take the exact value from the previous question. You get H1. But how about H2? How do we get H2? E. Wrong. Look at the question. Look what is zero? Working. Yes. So it says that you neglect the feed term, right? Meaning these are kind of not doesn't exist anymore. So meaning work in is 0. So h1 equals to h2. So you can directly use the term, the value h1 for so then you can calculate Q and thermal efficiency as usual. You just work out over Q, which in this case is actually just work out over Q. Now, so why can we do this? Of course, the main reason is because the question says so. I will say I can do that. So now, remember when I was teaching this, I told you one way for you to plot to sort of check whether your calculation of P is correct or not. I keep stressing that what about P is usually a very small value. The value normally don't be maybe not as 20 kilojoule per kilo. Then maybe it's sometimes 12 or maybe less than that. So that value is actually very small. So sometimes we just treat it as not significant because you see, let's say it is 10 kilojoule, meaning right, H1 is 190 something, that's it. Then this is just 200. The difference is not really that big. So sometimes if we measure the gap for simplicity sake, then it is at least good. Then, okay, so problem 3 and problem 4, right? They are still similar type of questions, so I will leave them for try. Problem 3 is a simple ideal cycle. This one will be more. For some reason, so this question, problem 3 is just another ideal cycle. This will be closer to the example that we did lecture, so you can try this out and practice. Then 4 also same thing is another repeat cycle. I think 4 is very similar to your example so we jump straight to 5. Okay? So like say 6 example early next Monday we can discuss. For problem 5, we jump from 5. Problem 5 is actually an actual repeat cycle. I think we didn't really touch that in the actual. Okay? So the steam power plant is designed to produce a net power output. So again, whether the question says net or not, if it says that the power plant is producing this much power, 99% of the time we are talking about net power. Okay? Because in a more complicated setup, the pump code itself is actually taken directly from the output. It's a self-serving thing. So like you just need a bit. It's like a car. You need a bit of power to kickstart it, but otherwise it just after that then it just starts working. So it's the same thing here. So that's why this is always referring to net. Okay, whatever comes out of the power plant is the net. So here this is going to be Brayton cycle. So steam enters a high pressure turbine cycle, and 10 megapascal, 500 degrees Celsius, and the low pressure turbine at 1 megapascal at 500 degrees Celsius. So steam leaves the condenser as a saturated liquid at a pressure of 10 kilopascal. So this is actually a very common thing. Like a very common thing. The 10 kilopascal and 10 kilopascal saturated liquid. The H is just 191.1. So assume the isotopic efficiency of the turbine is 80% and pump is 95%. Estimate the quantity of the steam and the turbine exit. B, the thermal efficiency of the cycle, and C, the mass flow of the steam. So again, B is just a common question, so I can define to be C. So now the main thing is A. So A, you need to find out the state of the steam at both of the exit of the turbine. So we have 2 turbines together. So we are not very sure whether at the exit of the turbine what state that they are getting, what kind of phase they are at. which is why this what the question says. If it is saturated mixture, you give it a quantity. If it is superheated state, then you give temperature. If it is saturated vapor, then it is saturated vapor. That's the question. So now we need to solve this first. So once again, let's start by drawing this with this cycle. So this cycle, just like what we just mentioned, we have no idea what is the exit of both the lines. So that time we don't worry too much about it. Just draw whichever way you like it, as long as it doesn't move really close. So now, don't forget, we are talking about an actual cycle here. So this 2s, there should be a 2 here. So this should be a 4s and 4 or 4a or 2a, depending on how you want to do it. Or b here, b mostly so right. Now, so one thing that you need to be a bit careful also is, so just now we mentioned, first question asks us to look for a state, right? This point. Right? So you need to be careful of one thing also, which is like you can also have a case where the isotropic version is mixture, but then I just have one problem. The actual one is superheated state. So then you might get this because the question says either one of them are looking for, so you need to be careful of this. Of course, we are always looking at the actual version, which is like 4, 6, 8. Okay, these just sketches. I have no idea what is this or what is this. So as long as I know who it is, it's fine. Okay, so this is 10 megapascal here. 10 megapascal. This is 10 kilopascal. Total net power output is 80 megawatt. Oh, okay. So we have 500 degrees Celsius here. This is 1 megapascal. Our output net is 80 megawatt. Okay, so if you would like to, you can also, like I said, follow step by step. You can always start from stage 1 if you want to. You can also start from stage 3 if you want to. So this question maybe over stage 3, so of course you can start from stage 3 by finding the two questions. But again, there is no actual order here. I will just not apply it. Even if the question, let's say H1 I give you a second half, this is the first half, it's fine, I will just count. So what is the number here? We can still start from H1 if you think that as the stage 1 if you think that's the easier way. So T1 is 10 kilopascal, saturated liquid, so we start from 1. Then so here below we can find H1. We can also find T1. Then from here, say 14 equals to T1, T2 minus T1, which is also equal. Okay. Now, this one is always the ideal one. Okay, so P2 minus P1 is always the isotropic version. It's not the actual version. So then we know that if we include the efficiency of the car, then This is the ideal one. So I just split this into two equations because my example in the lecture notes we skip this step. So might not be too clear. So here, okay. So this is actually H2S minus H1 if you are interested in looking for H2S. Okay, so if you are interested in looking for H2S, this equation actually is H2S minus H1. But we just skip it because we don't really need the H2S value. So if you sub this equation, you can get H2. So this will give you H2. So we complete this side of the equation. I mean this side of the graph. So now we move on to the other side. So for the other side, we know that T3 is 10 megapascal. T3 is 500 degrees Celsius. So from here, you can get H3. You can also get S3. Okay, so then we jump to state 4. So we know that T4 is 1 megapascal. And we also know that S4, S is equal to S3. So don't forget that this is the isentropic solution, not the solution. So based on this, what you found will be H4S. Okay, then you use the isentropic efficiency of the turbine to find H4. So you can get this for it. You have H4, you have T5 or P4. You can compare with the table to see what state it actually is. Now, so I think this one, I usually put the answer in for this turbine. I'll put it only for state 6, I think. So for this particular one, I think it is a sprinkler field. So you can check the H4 value again. So compare the H4 with the H G at 1 megapascal, then you can see which state it is at, then you can, and then you can give the temperature if it is equated state. Because either way, you cannot run away from this, then you know value. Actually, you need 5, you do have the value. Okay? So we jump to 5. So 5 is 1 megapascal. So T5 is 500 degrees Celsius. So from here, repeat the same thing. You can get H5, you can get H5. And once you get this, then you compare T6. Actually, the pressure will be right S because it's the same value. So you can compare T6 equals to 10 kilopascal. S6S equals to S5. Okay, so when you use, so now for this one, when you use the S5 value here, okay, let me just write out the value here. Okay. So S3 is, yeah, it's just for the comparison purpose. Then S5 is so if you use this S5 value at 10 kilopascal, you will see that this is actually a 所以就有一个 mixture. So to repeat the exact same thing as we did for the previous question, you need to find out what is X6S in order for you to find your H6S. So you still need to find H6S in this case and not stage 2 because otherwise you can't find H6. Because H6 you will need this equation. So from here you will get a new H6 value. Now this H6 value, when you compare to Hg at 10 kilopascal, you will have this exactly the same case as I was trying to tell you. You will see that it is actually a higher value than this. So meaning H6 is actually a superheated vapor. So in this case, if it is a superheated vapor, then you check what is T6 value. So T6 value is this value, which also means that you need to interpolate. Compare H6 at 10 kilopascal at the superheated vapor. Sound clear? Can everyone understand this? Basically, just it requires a lot of looking back and forth. Okay, so I will finish this first. So B, you need to find thermal efficiency. So as usual, thermal efficiency is just net over Q in or Q out over Q in. So you can either find Q out or Q in or work net. But in this case, I recommend work net. Why is that the case? Because in the subsequent question, you actually need to use work net instead. So you can just see. So if you have to find work net, then it is just work out minus work in, which means you need to find H5 minus H6 plus H3 minus H4 minus what is calculated. Then Q in is H3 minus H2 plus H5 minus H4. Okay, then C. So C, you need to find the mass flow rate of the speed. So the only term of information that we have that is related to mass flow rate is the net power output. So we know that the net power output is 80 megawatt. So which means that we also know that this will be equal to m dot work mass. Right? So yeah, so based on that, you take the work done value from the previous section, set it, then you can get mass flow rate. Just be careful of the unit because this megawatt when calculated should be kilojoule per kg. Okay, other than that, yeah, that is how you solve these equations. You want to consider getting a phone stand?
Huh? Hey, you bring? I borrow yours? You got yours?